Okay, thank you. First of all, I would like to thank the organizers for the kind invitation, and I enjoy my stay here at Lumini on this nice meeting. And as I announced in the survey, as announced in the abstract, I intend to give a survey on some research in this field. Of course, this cannot be complete because it's now a huge field of applications, and I will present only some parts of some results. And I'm trying to give some historical remarks concerning the first papers in this direction. If I am not complete, and if somebody of the participants here is not at my list, please, I beg your pardon. Okay, so the content is the following, the content of the talk. I have three sections. In the first one, this is a certain introduction concerning curvature measures in general. And then I will concern some stationary point processes of certain geometric sets. And these are things which are familiar to you, to many of you, from the point of view of convex bodies. Yeah, and we had heard already a few talks in this direction yesterday. And then I will turn to stationary random cell complexes. This is an extension of tessellations of random mosaics. And at the end, and this is, as I announced, the main part of the talk, I try to introduce some fractal extensions of these approaches. So let's come to the first part. I start not with convex geometry because there is a representation in another field in the differential geometrical context, which is a bit closer to that, but I will introduce a little bit later. And in differential geometry, one considers smooth submanifolds, say, in a Euclidean space, and one can introduce the so-called generalized, the Kate order mean curvatures. It's known from classical differential geometry, and for simplicity, I have considered here only the field in the presentation, only the case of full dimensional manifolds with a smooth boundary, say. Yeah? This is denoted here by MD, it's a d-dimensional manifold. This is a domain with smooth boundary, yeah? A bounded domain. And you can imagine this can be extended to lower dimensional submanifolds too, and there's also theory behind. And here the curvature measures or the curvature functionals of order K are introduced as integrals over the boundary of certain symmetric functions of the so-called principal curvatures. And the symmetric functions are recalled here again. Here in this line, yeah, we take the products of the principal curvatures of a certain order and sum them up over all these over all these tuples, and there exist certain constants which are known from convex geometry, which are appropriate to the whole. And if one integrates this over the surface, with respect to the surface area measure, this is Hausdorff measure of order d-1, one arrives at the curvature measures. And for completeness, one includes here special cases, namely if k is equal to d-1, then it's simply the surface area, then the symmetric function is equal to 1. Yeah, in this case. And for, as we heard yesterday, in the convex case for the order 0, this is the total Gauss curvature, the product of all principal curvatures, and this is equal in the topological context to the Euler number. This is also well known. Yeah? And as I mentioned, lower dimensional versions are available, and also you can extend this to local versions. If you add an indicator function of a Borel subset, you arrive at the measures. Yeah? This is the context of smooth geometry, and there are extensions to so-called piecewise flat spaces or piecewise smooth spaces via certain Morse index theory in an algebraic context, but I will not concern this here in detail because this is another field in a sense. Yeah? I will mention only some papers in the next part. So let's turn to the convex case. Now I would like to remember the so-called intrinsic volumes of the convex bodies, and here in this case, if K is a full-dimensional compact convex set, then the Kth order intrinsic volume agrees with this should not be the boundary, this should simply be of K of the whole body here. This is a misprint, yeah? The CK agrees with VK in the convex case, but only the definition is different, but they coincide with each other. You have two approaches, one within convex geometry, the other in differential geometry, but if your convex body has a smooth boundary, the values agree with each other. Yeah? This is also known. And here I mentioned some earlier papers when this development started concerning the convex theory. And maybe the first one to mention is Hartwiger's book from 1957. And then there are some following papers, in particular Rolf Schneider, who is here, extended this to measure versions, Hartwiger's approach. And I learned from that a lot when I was young. Postdoc, maybe. And yeah, and there are further papers, and I think an easy approach in the integral geometric context was given by Klein, who has, for instance, he proved in an easier way Hartwiger's characterization theorem, yeah, with his methods. And the inclusion-exclusion principle plays an important role when extending this to finite unions of convex bodies. Yeah? And this is, many of you know this theory, and this is the advantage of such a conference. I have not to introduce all these notions because you know them. And therefore we can go to the next slide. And this is an extension in the measured geometric context due to Federer in the late 1950s. There was an extension of these Kth order curvatures to so-called sets with positive reach. And a set with positive reach is characterized by the so-called unique projection property in a neighborhood. If you have a set with positive reach, say this one, then this means if you have a positive a neighborhood of a positive distance, say of distance epsilon, and in the epsilon neighborhood, you have the unique, no, this is not a good neighborhood, this one, you have the unique projection property. To each point in this neighborhood, there exists a unique nearest point here in the given set, whose distance is the smallest one, and this projection point should be unique. And this is if the reach means the largest, or the epsilon, which guarantees such a unique projection property. Yeah? This means reach of a set. And Federer extended these notions to sets with positive reach, but his definition was implicit. He used the Steiner type formula in order to introduce the extensions. And in the middle of the 80s, I have found an explicit representation, which is given here now in the formula. Here, this one. Namely, this looks similar like in the differential geometric context. You have to integrate, but this time not over the boundary of the manifold, but over the so-called unit normal bundle. You consider pairs, namely pairs of points from the set, and associated normals. Here, in such a point, if you have a smooth point at the boundary, you have a unit normal, yeah? A unique unit normal. But here at such points, you have a whole bunch. You have a normal cone, yeah? All these normals belong also to the normal cone. And you take all these pairs, and this is the unit normal bundle. And if you integrate over this unit normal bundle, which appears to be a rectifiable set with respect to the Hausdorff measure of dimension d-1 always, independent of the dimension of the set, the normal bundle is always d-1 dimensional. And then you integrate again some symmetric functions, but now not with respect to classical principal curvatures, but these are extended principal or generalized principal curvatures, which depend on the basic point and on the normal at the given point. Yeah? And one can introduce these extensions, and then if one takes these symmetric functions and integrates them up, then one arrives at that value which was given by Federer. Yeah? And this is a convenient expression because one can derive different formulas. And yeah, this goes back to 1860, it was published at least. And nowadays there are many extensions concerning such type of sets. But the extensions are always that way that you have again such a representation. You have a unit normal bundle, you can integrate some symmetric function, but in more general context, for instance, for the convex rings, you have to take into regard a signed multiplicity always. It's an integer valued multiplicity. And then you arrive at similar values, and these are the extensions, the additive extensions of the curvatures or the curvature measures in the localized version. Yeah? And I've collected here some names of people who have extended this. Maybe you can read it, but I should not give all the papers. If somebody's interested, I can give you the details of the publications. These are always publications, and there are different approaches, geometric measure theoretical approaches, and there are algebraic approaches. For instance, Bröcker-Kupper considered the algebraic method of Bernisch, and Fu is studying kinematic formulas, for instance, in the context of algebraic geometry, and so on. And I think the most general version is now, these are now the so-called VDC sets by Kornirata and Zajíček, and finite unions of VDC sets. And I think they contain at least many of those other models. Yeah? And all the applications in stochastic geometry I will present in the next slides can be considered in the more general context of one of these classes. Yeah? Here, when I started with this approach, I always considered finite unions of sets with positive reach, or locally finite unions of sets with positive reach. But we simply now, for the rest of the talks, we call them geometric sets, and they have all these properties I mentioned. Okay. And now I come to the first application. Maybe I should formulate some important properties of these curvature functionals. This is the additivity. It's well known to you from the convex setting. I denote the sets by x and y, and then you have the additivity property. This is for the functionals, and the same holds true for the measures. You have the additivity property. I present it in that way: y minus ck of x intersected with y, provided all these sets belong to the class under consideration. Yeah? And for instance, the convex setting, or in the case of sets with positive reach, and so on. Yeah, this is the additivity property, and this is used in order to extend the whole theory to finite unions. You could simply take the inclusion-exclusion principle and then extend the formula, but then you should show that it's independent on the representation. And this is a difficult part, but here the explicit representations plays a role. You do not need the inclusion-exclusion principle for a definition. Yeah? This is the advantage for the explicit representation. So this is the first important property, is additivity. Then you have motion invariance. You know that also very well. If you take a Euclidean motion, say G, apply it to the Z, then it is the same as ck of x. It does not depend on the place in space of the given set. This is additivity, motion invariance, and then you need a certain continuity property. This was the big problem here. For the convex setting. This is already solved in the very beginning. You take simply the Hausdorff distance, continuity with respect to the Hausdorff distance. But then it was a problem which type of continuity you should use for more general sets. And then it appeared that another notion from current theory for the normal cycles is appropriate, so-called flat convergence in a certain sense. Yeah? And if you use this, I will write simply continuity in a certain sense. Yeah? Then these three properties already characterize these type of functionals, namely any other functional, in the sense of Hartwig's characterization theorem, any other functional with these three properties is a linear combination of these one for different k. Yeah? And if you have a fourth property, if you have the functional has the scaling property like this ck, namely if you multiply by a real number, by a positive real number lambda, you're given z, then this is the same as lambda to the k times ck of x. This is known for the volume. By the way, the volume is included as a marginal case. The volume is simply for k equals to d, the corresponding expression. And the volume measure has this scaling property, surface area measure has it, and the other curvatures too. Yeah? And if a functional has additionally this scaling property, then it must agree with ck up to a factor, multiplicative factor. Yeah? These are characterizing properties and may be important for the rest, because all the applications, or most, not all, but many applications of the theory depend only, in stochastic geometry, depend only on these properties. And even on the fractal side, I'm always prey to the fractalist. You do not need to know curvature theory, you need only to know these properties. And you need some renewal theorem or ergodic theory, and then you can apply it to fractal geometry. Yeah, this is the advantage of this type of functionals, a complete system of certain Euclidean invariants in the sense of Felix Klein. Yeah? Okay, then now we come to the stationary point processes of geometric sets. It's in the sense of this type of sets I mentioned. And this is already studied, or has been studied for many years, and even we have here many talks on such subjects, and people are interested in different geometric properties. And I mentioned here some earlier papers or the books of some participants of this conference where these things are presented. And there is even, this was in the context of convex geometry. And there is an earlier paper of Favart and Santalot. They considered point processes of many submanifolds. Yeah, and they applied this to submanifolds in the smooth setting. And for sets with positive reach, I had a paper in 1986. This was a starting for applying this for sets of positive reach to stochastic geometry. And you know, one has many applications in, say, for instance, in stereology, mainly in the sense of kinematic formulas, or in the sense of more general integral geometric formulas. And I would like to mention a few examples. Maybe let's call these point processes marked point processes, where the marks are geometric sets. Let's call them Guérin processes, like it was usual at the beginning at least. And one has, if you have a stationary model, one can speak of, because the curvature measures are stationary, random stationary measures, you can speak of intensities. These are signed values, the intensities. And there's a relationship between the intensities of the primary point process model and the intersections with certain flats, say. Yeah? And here I considered in the example with the p-dimensional plane, EP. Yeah? And the intersection model is again a stationary model in the plane, and then you have again these curvature intensities, and there is this well-known identity between the intersection intensities and those of the primary set of different orders. Yeah? And these are known to you at least from convex geometry, yeah? These relationships. This is just CK-EP is the intensity of the kth curvature measure, which is locally finite here, of the intersection with the plane, and the CD plus K minus P is the corresponding intensity of the primary set. And this is for the corresponding relationship between the parameters K and here J, say, on the right-hand side. Okay, and in the special case of the Poisson model, if you take a Poisson process of geometric sets, then one has a formula which expresses the curvature intensity CK in terms of the typical cells, yeah? At the typical grains of the process. And CK is the kth curvature intensity of the whole model, of the union set. of this point process model. And then the other versions here, sorry, this lambda is the intensity of the germs, the mean number of points per unit volume. And the Cj bar, the boldface Cj, these are the mean values of the J total curvature of the typical J cell, of the typical grain, not J cell, we are still at the grain model. Yeah, we take it in the Palm sense. We take the typical grain, and this is a convex, this is a bounded set in this case, and a geometric set, and we test these curvature measures, and then we take, for instance, the total volume, the total surface area, the total Gauss curvature, and then one has an explicit formula of the intensities in terms of these typical cells, typical grains, sorry. You know, maybe some of you know these relationships for convex bodies. And this remains valid for all the other models. They have not been considered in the literature. In the past, I considered only the positive reach case, but the procedure is the same in the more general context. Yeah? This formula is always true. Okay, this is one example where this theory can be applied in stochastic geometry. And another example are cell complexes or tessellations. They also play a role here in this conference, and many people are considering tessellations, maybe tessellations generated by hyperplanes or by other models. We have heard yesterday certain construction. You have, for instance, Voronoi tessellation, Delaunay tessellations, and so on. Yeah? And there are some first papers in this direction also mentioned here. People always considered convex cells of the tessellations. Yeah? And by the way, this was a funny beginning of the story, why I got interested in these curved tessellations or point processes of geometric sets. In the early 80s, at the weekends, we used to walk with our children around the nature in our surroundings. And one fine summer day, I looked to the earth. It was very dry in the surrounding. I obtained on the surface of the earth a tessellation. And this tessellation was not convex. And the cells were of this type. Yeah. Imagine just crack structures. So, and all people were considering only convex tessellations. I thought, okay, we should try to do it for non-convex things, yeah. And it turned out this is possible, yeah, to do it. And also, if you, for instance, if you look to crack structures in materials, say in porcelain, China, I mean, yeah, then you also have such tessellations with non-convex cells, and you can even have non-smooth parts, yeah, with more, say, piecewise smooth parts also on, at least this would be a better mathematical model. And it turned out that one can do that too. We started to work on this together with Viola Weiss, and the first paper appeared in 1988, and we considered stationary random mosaics with whose cells were of positive reach. Yeah? If the cells are positive reach, are manifolds, submanifolds of positive reach, then it turns out that these are at least Lipschitz manifolds, but one can see also more general cells, and this remains valid. And later on, I studied, this appeared in the same year, but the order, the historical order was different. We started with Viola, and then came the arbitrary cell complexes. And cell complex means you do not have a tiling of the whole space, yeah, or a tessellation, but you have only a complex of cells, and they can be different. You can have cells, two-dimensional cells. You can have some one-dimensional, and so on. Yeah, and you need only the topological structure of a cell complex. Maybe it's known to you. You have the so-called skeletons, the eye skeletons. In this case here, the eye skeleton would be all these one-dimensional cells together with this one, and this one, and this. Yeah? This is the eye skeleton. The two skeleton is this one, and in higher dimensions you have the corresponding different skeletons. And you can consider a stationary model. You can again try to obtain some mean value relationships. Of course, nowadays it's more interesting to consider higher order moment measures, but at that time we studied mean value relationships. And here for such cell complexes, you have again relationships like in the point processes models, but here these relationships are a bit more stringent. You have relationships between the Kate curvature intensity of the eye skeleton, the CK sub I, this is the eye skeleton, the Kate curvature intensity, and this is an alternating sum of the corresponding values of the typical jade cells, the total Kate curvatures of the jade cells, but you need to know all jade cells of dimension up to I. Yeah, and the Nj are the mean number of J cells per unit volume. And then you have such an alternating sum. And this is, by induction, you can take an inverse formula. You can express the intensities by means of the Palm values, the typical cells. And in the opposite direction, you can take the values for the typical cells and can express them by means of the curvature intensities. Difference of two curvature intensities is here on the right side. Sometimes it does not work, the pointer. No. Here, this one. And this formula remains true for the more general cell complexes with an arbitrary geometric structure, like I mentioned in the introduction. This is another application concerning the jade cells or cell complexes. Now I will turn to fractal models. Of course, one could try to find moment relationships also for these more general models, but I looked to the literature. Unfortunately, people do not consider, people working in stochastic geometry do not consider these smooth cells or non-smooth cells. Mainly they consider flat tessellations, yeah? But this is possible. Of course, the flat models play an important role in digital images and so on, and very important Voronoi-Delaunay tessellations, they are very important for many applications, but for crack structures, these non-smooth models are also important. Yeah? Okay, now come to the fractal models. Of course, if you take fractal say topological manifolds or more general fractal sets, you do not have these classical values for curvatures. But many fractals, at least those which have been studied in the last years, and these are not many because their structure is in general very difficult, but if you have certain self-similarity properties or self-conformal properties, then it's possible to do. And there's one main background for applying the former theory. This is, at least in lower dimensions, the theorem of Joseph Fu, who is known to many of you. Namely, in low dimensions, up to dimension d equal to 3, if you take any compact set, an arbitrary compact set, and take the epsilon neighborhoods, then it is true that for almost all epsilon, Lebesgue, almost all epsilon, the epsilon neighborhoods, they do not have positive reach, but the closure of the complement has positive reach. Yeah? This is here, K epsilon is the epsilon neighborhood, and then takes the complement of K epsilon at the right-hand side. Here. Sometimes this pointer does not like my slides. No, okay, take the last formula on the right-hand side, and then you take the closure, yeah? Then Fu showed that they have positive reach. And then you can apply the former approach. You can determine the curvature of those sets, but you do not like the complement set. You would like the former, the primary parallel set, K epsilon, and then there is a reflection principle, which is known from the smooth theory or from the convex. From convex geometry, the reflection principles cannot be applied, but in the smooth case, then you take simply this of the complement set, and you should add an assigned factor minus to the d minus k, and then you arrive at a right notion for the curvature of the parallel set. Yeah, this is an appropriate notion, and this can be included in a more general approach, which we have developed together with Jan Rataj. And then we try to consider these parallel sets here in the fractal case. And we try to find some limit as epsilon goes to 0. If you take a classical set, a convex body or a smooth submanifold, then you know that the curvature methods converge. This can be shown, yeah, to those of the primary set. In a fractal set, you have oscillation or explosion, whatever. Yeah, you do not have a limit. But you can try what you are doing always in physics, rescaling. Yeah? And then one can try to find a notion which is appropriate. And this was first done by Stefan Winter, who is here, who will give a talk in this afternoon. And he considered the deterministic case. He considered certain classes of self-similar sets. I will introduce a little bit later what is meant by this. He showed that under certain conditions, this limit exists if you take the right rescaling. Namely, if epsilon is the distance, then you take epsilon to a certain power. And the power depends on the dimension of the fractal set, it's the capital D, and the order of the curvature, this is the order K. Yeah? If you take this rescaling, then he could show that under certain conditions such a limit exists, and this was introduced as the K fractal curvature of the given set F. Or if this, under more general conditions, you should take the average limit. You take averaging with respect to epsilon, with respect to a Dirac type measure, which is presented here. Yeah? And he considered these things under the so-called open set conditions, and under the conditions that the parallel sets are polyconvex. These things were developed at that part in the polyconvex setting, but it turned out one can consider also non-convex, polyconvex parallel sets. And I will briefly present this approach just in the next slide, after the next one. And there is also an stochastic applications. We can consider a stochastic model, and I will give some details on the stochastic model. It's the following. But first, I would like to present some results of Stefan. This was based on his PhD thesis. This paper appeared in 2008. He considered two carpets, Sierpinski carpets, which have the same Hausdorff dimension, and they cannot be distinguished by means of the Hausdorff dimension, but they have a different topological structure, as you can see, and they have also a different. Here in this case we have only two. We have C0 and C1, and C2 is already dependent on C1. So we have two parameters, two free parameters in this case. The Hausdorff dimension is the same, but on the right-hand side you have a little bit less holes heuristically than on the left-hand side. Yeah? And it turns out that the number of holes corresponds to the Euler number in a sense. In the limit can be expressed in the expression for Z0. The fractional value is 0.016, and in the other case it is 1,4. This 1,6 you have more holes in a sense, and 1,4 you have less holes. And the other one, C1, somehow expresses the boundary length of these cells in the limit, and on the left-hand side, this boundary length, because of less holes, it is a bit less than on the right-hand side. Is also expressed on the right-hand side is a bit less than on the left-hand side. It's also expressed in terms of the values. And though you have two new parameters which help you to distinguish between fractal sets, of course, you need a lot of digits for the distinguishing, but it's possible. Okay, now let's turn, I have not much time now, to the random setting. I briefly express it. There are some conditions, maybe not so important to look to the details. At least self-similar random sets are generated by a random number of random contraction similarities. And this is S1 up to S nu. And this is a new tuple of which can be dependent of each other. The S1 can, S2 up to S nu, they can be dependent, but it's one tuple with a certain probability distribution. And the number nu is also given as a random number. Yeah? And then you take the following. You construct the so-called Gaussian-Watson tree of such similarities. Namely, you start with one new tuple, and then for each member of this tuple as one, you adjust a new tuple of the same type with the same distribution of similarities of the same time. With S2, you also adjust, to S2 you adjust another tuple, and you need two indices now. The first index tells you the parent number, and the second index is the new generation, yeah? And you take a whole bunch of new tuples, and the number new can also change from step to step. But you can construct in such a way, and you continue this procedure. Again, you add some independent. They are independent. The tuples are independent of each other. Yeah? But inside the tuple, the constructions can be dependent. Yeah? And then you take an infinite tree of such similarities, and then you can construct a random set. Namely, you take the following. You take a starting set. This is a given primary set from the so-called open set condition. This is denoted here by J. And you apply, you go along such an arrow line. Now you go along such a line here, yeah. So and you apply iterated these similarities to the primary set, and the set gets smaller and smaller. And you take all these. The union for the end step of all these new points or new sets, and then you take the intersections with respect to the stage end, the time step, and this generates a random compact sets because the primary set J is also compact, and this has a so-called stochastic self-similarity property, namely the random set F has the same distribution as the union of new independent random sets with the same distribution of F. Yeah? And this is a stochastic similarity. And it turned out for such constructions, one can, this was already given before, one can calculate the Hausdorff dimension with probability 1. The Hausdorff dimension is given by this equation, the expectation of the random contraction ratios to the number d. This is the unique d for which this expression is equal to 1. This is the Hausdorff dimension. This was given by several authors under different conditions. And, and if you use this, one can prove the following. The first paper was given by Gatsuas. He considered the case of the Minkowski content. Namely, he took the Lebesgue measure of the full parallel set divided by or multiplied by epsilon to the Hausdorff dimension minus dimension of the space and considered the limit. And he obtained that this limit exists under certain conditions, and this was the so-called Minkowski content. Yeah? And the extension to curvatures are the following. In higher dimension, one has to assume, at least we assumed up to now, that the parallel sets have this nice property. In lower dimensions, it's always true. The conjecture is for random self-similar sets with all these conditions is always true, this first condition. And in Steffen's paper, the polyconvex situation is also good. In this case, also always true. And in this case, the random fractal curvatures can be determined. We have certain other conditions. Maybe I skip this. If somebody is interested, we can go to details. And one knows there is an auxiliary random variable. This comes from Galton-Watson theory. Namely, one knows from martingale convergence theorem that such a limit of sums of these products of contraction ratios exists with probability 1, and this random variable has expectation 1. And then one considers an auxiliary measure. This is determined by the logarithmic contraction ratios, denoted in the expectation of those distributions. And then one can show the following. If the measure mu is non-lattice, it's from renewal theory, then one can show the same like in the Minkowski case. One takes the rescaled limits one can consider either the expectations or the corresponding convergence with probability 1. In both cases, the formula expresses some fractal variance. One has the mean value result, and one has the probability 1 result. And one has that such a limit exists. But here it comes in the random value, the random number x, the real number x, non-negative real number x additionally. And if the measure is non-lattice and if the measure is lattice, one should take again average limits in the sense of mean values or in the sense of convergence with probability 1. And though one has random fractal curvatures for the model, and one can also localize this to measures. This was also done. Yeah? One has results for fractal curvature measures, and one has some integral expressions for the limits. But the integral expressions are quite hard for computer applications. Yeah, this is not so easy for some simple models. Is easy to do, but in general, these formula are not very useful. And the background for proving this is an extension of the classical renewal theorem to Euclidean to a random variant, and some applications to fractals. Yeah. And we have nowadays also many other results in the fractal study. I mentioned here some recent papers starting in the early 2011. These are the first papers of the extensions. And we are preparing a book with my colleague Jan Ratay, and in chapter 11 there is a survey on all these results, and also some ideas are presented and some proofs for beginners, yeah, in order to give an introduction. Okay, and so I think I'm sorry, I'm a bit at the end of the talk, so we have no time for discussion, I think. Oh.